In a plant, a lot depends on the reliability of equipment. The failure of just one part can critically affect the plant as a whole and all the people in it. When machines and components are taken down for maintenance, we've got to inspect each part before reassembly, and a visual inspection is just not good enough. To prevent equipment failures, we use direct inspection methods that make flaws stand out on the surface, or indirect tests that give us a picture of the inside of the part. Now, these methods are called non-destructive testing. They reveal the presence of any defects that might lead to the failure of a part, and they do it without damaging the part in any way. Non-destructive testing methods use all kinds of things to search for defects: magnetism, sound, X-rays, and light. Today, we'll be discussing 4 non-destructive testing methods that are often used in the plant. These 4 are magnetic particle, ultrasonic, radiographic, and liquid penetrant. The magnetic particle test, mag particle for short, can only be used on metals like iron or steel that can be magnetized. In the mag particle test, the entire part is magnetized and then sprinkled with a very fine iron filings. A defect is indicated where the iron particles clump together. In ultrasonic testing, the second method, a high-frequency sound wave is sent through the part being tested. When the sound wave hits a flaw, it bounces back and shows up as a blip on a screen, much like a sonar scope. Radiographic testing is similar to taking an X-ray of someone to check for broken bones. The same kind of equipment is used, and the same kind of precautions are necessary to protect personnel. The fourth kind, the liquid penetrant test, is also called dye penetrant. A dye is put on the part to be tested and given time to accumulate in surface cracks. Then a developer is used to draw the dye out to the surface and make the location of the flaw visible to the examiner. Mag particle, ultrasonic, radiographic, and liquid penetrant, each technique is alike in one very important aspect. Each test relies on an examiner to interpret the results. Now, the examiner must determine whether a defect actually exists. If a flaw is present, a decision must be made as to whether or not the flaw is relevant to the reliability of the part. To do this, the examiner must have the best data available. This means that the part being tested has to be free of any material that might indicate a non-existent flaw, or even worse, cover up the indication of a defect. To prepare a part for testing, it must be cleaned properly and thoroughly. Parts can be cleaned with detergents, solvents, or by abrasive blasting. And once the part is clean, the examiner will be able to interpret the results of the test more easily and accurately. The choice of which test to use is an important consideration. Each non-destructive test has its limitations. The mag particle test, for example, can only be used on materials that can be magnetized. So on aluminum or ceramic parts, you'd have to use one of the other 3 tests. Dye penetrant tests only reveal surface flaws. For deeper defects, an indirect test must be used, ultrasonic or radiographic. But ultrasonic tests are difficult with irregularly shaped parts. The beam is reflected from every interior surface. Radiographic techniques are hazardous and require expert interpretation. From these examples, you can see that the selection of a test depends on the shape of the part, the material it's made of, and the type of flaw we're looking for. And so far, we've looked at non-destructive testing in general and talked about the importance of preparing a part for examination. In a moment, we'll start to discuss each of the 4 methods in turn: mag particle, ultrasonic, radiographic, and dye penetrant. But before we go on, take a break to read through segment 1 of your text. Magnetic particle inspection is a direct, non-destructive testing method that is a quick and easy way to test large iron or steel parts. It takes longer to set up for than dye penetrant, but it'll detect some subsurface defects as well as surface flaws, and it's quicker on large components. Let's see how it works. We magnetize a piece of steel by making an electromagnet out of it. An electric coil is wrapped around it, and when electricity is passed through it, it becomes a magnet. Any cracks or flaws create a disturbance of the magnetic field that concentrates the field near the flaw. If we sprinkle iron particles on the magnetized metal, they'll collect in the magnetic field, and since the field is concentrated near the flaw, they will concentrate in the area of the disturbance. The surface indication not only shows the location of the defect, but also tells us something about its size and shape. Now let's run through a typical magnetic particle test to see the procedures actually used in the plant. We'll use this weldment for our demonstration. First, the part is thoroughly cleaned by abrasive blasting. The next step is to hook up the cables from this machine and set the current level. This is basically a transformer that's capable of putting out a high current, thousands of amps, at a very low voltage, less than 20 volts. Even though it's only 20 volts, don't ignore the possibility of a shock. There are two different ways that the part can be magnetized electrically. This kind of hookup is called a head shot or contact shot, and it's even simpler than the example we've just seen. Here, the current runs straight through the part, and it magnetizes the part this way. The magnetic field runs at right angles to the direction of the current. Cracks that run at right angles to the magnetic field are detected by this method. The other method is called a coil shot. The current runs around the part, and the magnetic field now goes along the length of the part. This reveals cracks that run this way and this way. Both kinds of tests are necessary to completely check the part. For a contact shot, it's extremely important to make the connection tightly. If they aren't tight, the contacts will arc and try to weld themselves to the part being tested. And once the current is set at the appropriate level and contact is secure, the magnetic field is energized from the remote control on the probe's handle, and the particles are sprayed on. If visible particles are being used, the indication of a flaw would show up immediately. But since we're looking for hard-to-locate flaws, we're using fluorescent particles in this test. When the part sprayed with fluorescent particles is exposed to black light in a darkened room or workspace, defects show up glowing green. Mag particle testing can be used for parts of any shape or size and can detect flaws running in any direction, on the surface of the part or close to the surface, by using both kinds of hookups: a contact shot and a coil shot. The two limitations of magnetic particle inspection are that, first, it can only be used on metals that can be magnetized, like iron or steel, and second, it can't show up really deep flaws. And though you probably won't be performing this kind of test yourself, you may be called upon to assist a technician who is a specialist in non-destructive testing. Your greatest value to him is in the preparation of the parts to be tested. Remember, the cleaner the parts are, the better he'll be able to accurately interpret the results of the test. And the reliability of some critical components may depend on that interpretation. Take a break now to go over the material in segment 2 of your text. If you have any questions, ask your instructor, who will be able to tell you how mag particle tests are used in your plant. And when we return, we'll be looking inside some parts, indirectly, with ultrasonics. Mag particle testing is a direct method of non-destructive testing. It's direct because the indication of a defect shows up on the part itself. Mag particle can detect some subsurface flaws, but for really deep flaws, an indirect method must be used. Ultrasonic is one type of indirect test that's used to find subsurface defects. Ultrasonic testing is indirect because instead of a defect showing up on the outside of the part, it's seen on a screen like this, or the thickness of the part registers on a digital readout like this. Ultrasonic testing uses sound waves pitched far above the limits of our hearing. A device called a transducer makes the sound waves. Now, these sound waves travel through the material being tested and bounce off the opposite surface. The transducer then acts as a microphone to pick up the return signal. If there is a flaw in the material, it will also reflect the sound waves back to the transducer. This signal comes back sooner than the reflection from the opposite surface. By measuring the amount of time it takes for the signal to bounce back, we can determine the depth of the flaw. Now, this flaw detector electronically converts the returning signal into a display onto a screen called an oscilloscope, which is similar to a television screen. Let's see how it's used in practice. We'll use this test piece to show how the detector works. First, we clean the piece with solvent to avoid incorrect readings. Next, to get a good connection between the transducer and the material, we use a liquid called a couplant. The couplant eliminates any air between the transducer and the metal so the sound waves can pass through at full strength. Many different liquids can be used as a couplant. In this case, we're using a light oil to make the connection. We'll apply the probe to this part of the test piece where there's no irregularity and calibrate the scope. The blip on the left side of the screen represents the reflection from the surface in contact with the transducer. And that's called the initial pulse. This blip represents the back reflection, the signal that bounces off the opposite or reflecting surface. The distance between the two blips on the screen represents the total thickness of the piece. We can adjust this distance so that our view of the part fills the whole screen. We can also match the spacing to the scale at the bottom. The test piece is 4 inches thick at this point. We can show 4 units between the incident pulse and the back reflection. Or for metric measurement, we can use a scale that shows the distance at about 10 centimeters. And now that the scope is calibrated, let's see what a defect looks like on the screen. When the transducer is moved so that it's directly over this hole, you can see that the initial pulse and the back reflection are still there. But there's another blip that shows up in between. This blip shows the location of the defect. On a scale of 10, it shows up at 6 3/4. Sure enough, the hole in the test piece is 6 3/4 centimeters from the top. If we move over to the next hole, the blip is still in the same place, which means that this hole is drilled at the same depth. This time, though, the blip is larger because it's a larger diameter hole. Ultrasonic testing not only shows the location of a flaw, but also indicates its relative size. However, it's not easy to use, and it takes a fair amount of experience to interpret the readings properly. There's another ultrasonic technique that's much easier to use. This is an ultrasonic thickness gauge. You may be using it on the job to check the thickness of parts like boiler tubes. The thickness gauge is calibrated against the known thickness at this pad on the front on this meter. It's 250 thousandths. To calibrate the ultrasonic thickness gauge, put a drop of couplant on the pad and then firmly press the transducer against the metal. And then adjust this knob until the readout shows 0.250. The meter will now give an accurate thickness measurement. Now, to check a tube wall for erosion, Spread couplet over the tube. Now, this tube has been cleaned. In a boiler, you'd probably have sandblasted it clean first. At specified intervals, take measurements around the diameter of the tube. Record each measurement carefully so they can be compared with the known thickness of a new tube wall. If the walls are too thin, the tubes must be replaced. Sometimes you may have to take measurements more than once because readings can vary if you don't use firm, uniform pressure to hold the probe against the material. Doing it right so you'll get accurate, consistent readings takes some practice. When you move the probe over an eroded spot, the readout changes to show the change in the thickness of the wall. Ultrasonic testing is a valuable technique for locating hidden defects. In this section, you've seen how the two kinds of ultrasonic devices are used, the flaw detector and the thickness gauge. Next, we'll discuss another indirect method of testing, radiographic inspection. As you'll see, radiographic testing is a powerful tool for flaw detection, and it requires some very important safety precautions as well. But before we go on, take a break to go through segment 3 of your text. Ultrasonic testing is one kind of indirect testing where the indication of a flaw is seen on an oscilloscope screen or a digital readout. Now, we're going to look at radiographic testing, sometimes called X-ray testing. It's also an indirect method. The results are seen on a piece of film or a fluoroscope screen. Radiographic testing has several advantages over the other methods we've discussed. It not only reveals the location of the flaw and its size, but also shows us the shape of the defect. Knowing the location, size, and shape of a defect can be very important when making a decision as to whether a part is serviceable or if it has to be repaired or replaced. The main disadvantage of radiographic inspection concerns safety. Everyone in the area of a radiographic test must be protected from the radiation used to perform the inspection. Now, basically, radiographic testing is similar to a medical X-ray. Just as you have to remove any clothing with snaps or zippers that might show up on the X-ray, the part being inspected must be free of any foreign material that might show up and raise a false indication. Now, here's how radiography works. Rays from an X-ray machine or a small piece of radioactive material pass through the test object and expose a piece of film on the other side. Or, in some cases, a fluoroscope screen may be used to give an instant view of the inside of the part. Whichever method is used, it takes an expert to interpret the results. Whenever radiographic testing is going on, radiation protection is our #1 concern. The equipment is handled very carefully to avoid accidental exposure to the beam, and sometimes safety precautions require personnel to leave the area where testing is taking place. Where radiation is a hazard, you'll see a sign like this to warn you to stay away from the area. Anyone involved in the testing itself wears devices that measure the amount of radiation received. And that way, everyone working with radiation is monitored to make sure they don't get an overdose. This kind of testing is done only by experts. Radiation is nothing to play around with, and you won't see experts taking chances. When you're called in to assist them, take the hint. Needless exposure to radiation can definitely be hazardous to your health. Now, so far, we've seen 3 methods of non-destructive testing that are usually done by specialists: magnetic particle, ultrasonic, and radiographic. In most cases, You'll be helping to perform these tests, not doing them yourself. Now, in a few minutes, we'll be talking about another kind of test that you will be doing on your own. But first, take a break and study the material in segment 4 of your text. Liquid penetrant testing is one of the most common types of direct, non-destructive testing. You'll be doing it yourself occasionally. This method, also called dye penetrant, uses a visible or fluorescent dye mixed with a light oil to penetrate surface cracks. After allowing time for the penetrant to soak in, a period of time called the dwell time, the excess dye is removed from the surface of the part with a lint-free wiper dampened with a solvent. After the excess dye is removed and the solvent is dried up, a developer is sprayed on the part. The developer is a very fine talcum powder that draws the dye out of the cracks, and it shows up in the developer. The indication not only shows the location of the crack, but also gives an idea of the shape and size of the defect. When a visible dye is used, the indication shows up immediately. With a fluorescent dye, a black light is used to make the indication of a flaw glow green. Dye penetrant testing will only expose the indication of a possible crack when the flaw is on the surface of the part. So this test is generally used on parts where experience has shown that surface cracking is likely to occur. If an indication of a defect is found, the part may be tested again with another method to define the nature of the flaw. Any test is only as accurate as the person interpreting the results. Unlike some of the other types of non-destructive testing we've discussed, it doesn't take an expert to do a liquid penetrant test. But it does take a little practice to become familiar enough with the technique to be confident of your own accuracy. Let's go back over the procedure step by step. A dye penetrant test can be used on almost any kind of material, metal, plastic, or ceramic, as long as the part has a finished surface. For our demonstration, we'll use this turbine blade retainer pin. The first step is to clean the part. Using abrasive blasting, detergent, or solvent, clean the part to be tested as thoroughly as possible. If the part isn't completely clean, the test may still work, but the cleaner the part, the more accurate the test and the easier it is to interpret the results. Next, choose a penetrant. Usually a red dye is used, but sometimes a fluorescent penetrant is employed to show up extremely small cracks in a finely finished surface. Read the manufacturer's directions and follow the instructions for application. Spray the area to be tested from 8 to 10 inches away. That's 20 to 25 centimeters. Get a good, even coating on the surface of the part. Now, give the dye time to penetrate any cracks. This dwell time varies from material to material. It also depends on the kind of flaws you're looking for. Find out the necessary dwell time by checking the manufacturer's instructions or asking a supervisor. For most tests, manufacturers generally recommend a dwell time of 8 to 10 minutes. After waiting the right length of time, dampen a rag with solvent and remove excess penetrant from the surface of the part. Don't spray the solvent on the part. You don't want to wash the dye out of the cracks. When the surface is clean and dry, apply the developer according to the directions from the manufacturer. Now, as you can see, the developer has drawn the dye out of the crack, and a clear indication of the flaw shows on the surface. This is what you're looking for when you do a liquid penetrant test. If you discover any indication, report your findings to a supervisor. Depending on the part, it may be tested again with some other method to determine whether the flaw is serious enough to demand repair or replacement of the part. The liquid penetrant test is commonly used because it's quick and easy to perform. This test, however, has some important limitations. For one, the dye only reveals surface flaws. It doesn't give any indication of any defects inside the part. Two, this test is only effective on finished surfaces. A raw casting is too porous. The penetrant would seep down into the pits on the surface. That makes it pretty hard to interpret results. The whole piece would look like an indication. Well, you can see that each method of testing has good points and bad. Magnetic particle inspection can only be used on metals that can be magnetized, iron and steel. And the test takes a little while to set up, but it's a quick test for large parts, and it's sensitive enough to detect extremely small defects. Ultrasonic tests can reveal deeply hidden flaws, but they're difficult with irregularly shaped parts, and results are often hard to interpret. Radiographic inspection gives a detailed picture of the inside of a part and requires elaborate safety procedures. With any method of non-destructive testing, safety comes first. Abrasive blasting can be dangerous if someone is careless or forgets to wear their eye protection. And some solvents are flammable or give off fumes that can be a breathing hazard. Aerosol sprays can be dangerous too. The sprays used for dye penetrant and mag particle inspections carry the active ingredient in a fine mist of oil. If the oil gets in your lungs, it can cause serious problems. It can even be fatal. Some kinds of liquid penetrants and mag particle tests can also be hazardous to your eyes. The methods that use black light to make fluorescent dyes or particles show up have to be handled carefully. Black light is really filtered ultraviolet light, the kind of light that gives you sunburn. The filter protects you somewhat, but if you're careless enough to look directly into the light, you can literally sunburn your eyes and cause permanent damage to your vision. All these methods of non-destructive testing are safe, providing you use common sense and don't overlook basic safety precautions. So before you start, read the directions on the equipment and the manufacturer's instruction manual. And it's a good idea to check your plant's safety manual too. When properly used, non-destructive testing helps keep the plant running safely and smoothly. By learning to use these methods carefully, you're doing your part to help keep your plant operations safe and reliable.